Hello everyone, and welcome back to the Fluctus Channel. NASA's Artemis program is built to send astronauts beyond low Earth orbit and prepare for future moon missions. At the center of that effort are the Orion spacecraft and the Space Launch System rocket, or SLS. Orion is NASA's crew capsule for deep space, while SLS is the heavy lift launcher designed to send it toward the moon. Artemis I was the first full test of that combination.
Go for launch. At this time, I give you a go to resume count and launch Artemis I.
The uncrewed mission sent Orion into deep space, around the moon, and back to Earth after more than 25 days in flight. After splashdown in the Pacific, recovery teams brought the capsule aboard a U.S. Navy ship. Artemis I proved the spacecraft, rocket, and recovery process could work together. But Artemis II will be the real test. That mission, which took place early April 2026, was the first crewed Orion flight. Four NASA astronauts completed the journey in almost 10 days, marking the first human flight to the moon's vicinity since 1972. Even without a lunar landing, Artemis II is one of the program's most important flights because it proves Orion can safely carry people through launch, travel, re-entry, splashdown, and recovery.
Yes. Do it. Say it. Yes! Let's go!
That means NASA is not only testing the rocket and spacecraft, it is testing the entire human system inside the capsule, including the seats, harnesses, suits, displays, and emergency procedures.
For these awesome, I'll call them drink notes.
For astronauts, the hardest moments may not be the quiet days in space, but the violent phases at launch and ocean landing. That is why NASA has been putting so much effort into testing its astronaut suits and seat systems. During launch aboard SLS, the crew is shaken by vibration, noise, and acceleration as the rocket climbs away from the pad. Then, after traveling around the moon, Orion returns to Earth at extreme speed, deploys parachutes, and hits the Pacific in a powerful splashdown. Even a normal landing can send heavy loads through the astronauts' necks, backs, shoulders, and legs.
Welcome home. Christina, welcome home. Yes!
So NASA had to do more than make sure Orion survived. It also had to make sure the people inside do not suffer injuries during those sudden impacts.
Thank you.
To solve that problem, NASA partnered with the Air Force Research Laboratory, or AFRL, where engineers study how the body reacts under impact. They tested Orion's crew survival suits and seat designs under conditions meant to simulate what astronauts could feel during landing and recovery. This is not just about comfort. It is about controlling how the body moves when the capsule suddenly stops. The seat has to absorb energy and spread out force. The harness has to hold the astronaut firmly in place without creating new injury risks. The suit has to support the body, protect life support connections, and still allow enough movement for astronauts to do their jobs. Inside the lab, the process looks like a space-age crash test. Orion seat setups are mounted on specialized rigs, and test subjects or instrumented dummies are strapped in while wearing the suits. Researchers then run controlled impact scenarios to recreate the forces expected during splashdown. These loads are studied in multiple directions because the capsule may not hit the water in one perfect straight-down motion. The impact can push the body downward, sideways, forward, or backward. Sensors measure how much the head snaps, how the torso bends, and how much force travels through the spine. If the helmet moves too violently or the seat cushioning fails to manage the load, engineers can adjust the design before Artemis II flies. That work matters because Artemis II is much more than a symbolic trip around the moon. It is a full mission rehearsal for later flights that will push farther toward lunar landing operations. NASA needs to know that Orion's systems can support astronauts from launch to recovery, not just in theory, but in real conditions with human occupants. Computer models help, but they cannot replace physical testing with real suit geometry, seat positioning, and impact behavior. A small design issue in a harness, helmet clearance, or seat load distribution could become a major problem during splashdown. These tests help engineers find weaknesses early and improve the hardware before flight. Recovery operations are another major part of the challenge. Once Orion lands in the ocean, the astronauts may be tired, disoriented, and physically stressed after launch, spaceflight, re-entry, and impact. That is why NASA and the Department of Defense also had to practice astronaut recovery at sea. Ships, helicopters, divers, and support teams rehearsed how they would locate the capsule, secure it, assist the crew, and bring both astronauts and spacecraft aboard safely. In the end, NASA's G-force protection suits are not just flight clothing. Combined with Orion's tested seats and restraints, they are part of a survival system designed to protect astronauts through some of the most violent moments in modern exploration. After proving how astronauts may survive the brutal forces of launch and splashdown, the story of American space testing continues with a spacecraft that has no crew at all. The X-37B orbital test vehicle is a small, reusable military spaceplane operated by the U.S. Space Force, built to launch like a spacecraft, operate in orbit like a satellite, and land on a runway like an aircraft. Since its first mission in 2010, the program has steadily expanded both its ambition and its endurance. As of 2026, the X-37B has launched 8 missions, completed 7, and pushed its time in orbit from 224 days on its first flight to a record 908 days on Mission 6, while Mission 7 landed in March 2025 after demonstrating operations in new orbital regimes and a recovery at Vandenberg Space Force Base. That long-duration capability does not begin at the launch pad. Before the X-37B ever leaves the ground, crews carefully transport the vehicle across the facility in a protected configuration and prepare it for integration with its rocket. The handling process looks very different from a normal aircraft tow, and very different from the way most satellites disappear into a fairing. The X-37B sits somewhere in between those worlds. It must be moved, inspected, and mounted with the expectation that it will eventually come back down, be opened up, studied, and potentially flown again. That reusable character is one of the program's biggest advantages, because experiments do not just go up into space and stay there. They can return to Earth for direct inspection after months or years in orbit.
Main gear touchdown. The nose of the shuttle being rotated down toward the flight deck. The parachute being deployed.
Once the vehicle is mated to its rocket, the mission shifts from aircraft-style preparation to full launch operations. Earlier, X-37B missions flew aboard United Launch Alliance Atlas V rockets. While later missions expanded to more powerful boosters, including Falcon Heavy for Mission 7 and another SpaceX launch for Mission 8. That progression shows how the program has grown from an unusual technology demonstrator into a more flexible orbital test platform. The vehicle's missions have included testing future space technologies, studying material performance in orbit, and experimenting with new operating concepts. Then comes the part that makes the X-37B so different from most spacecraft. It returns to Earth and lands on a runway. Instead of splashing into the ocean under parachutes, the black, winged vehicle glides home like an unmanned spaceplane and touches down on landing gear. That kind of recovery gives engineers a major advantage. They can inspect heat shield materials, structural surfaces, avionics, payload systems, and onboard experiments far more directly than if the mission ended in the ocean. Another major part of America's military space effort is less mysterious, but no less important: launching the satellites that support everyday military and civilian life. Among the most critical are the GPS-3 satellites, the newest generation in the Global Positioning System constellation. These spacecraft underpin navigation, timing, weapons guidance, aviation, and countless civilian applications around the world. Because of that, even getting one to the launch site is treated like a strategic operation. Space Force footage shows GPS-3 satellites being flown to Florida aboard C-17 Globemaster, including later models such as SV-06, which arrived on the Space Coast under careful handling and tight security. Once the satellite reaches Florida, the next phase is just as deliberate. The spacecraft is offloaded with extreme care, kept in controlled conditions, and moved into processing facilities where engineers prepare it for launch. These satellites are designed to improve the constellation with stronger anti-jam protection, improved accuracy, and upgraded capabilities for both military and civilian users. These advanced machines and extreme operations demonstrate just how broad America's space exploration efforts have become. And as they continue to push the limits of what is possible in that field, it is difficult to predict just how far they will go. Different spacecraft, different missions, and different crews, but all part of the same larger attempt to master launch, survival, recovery, endurance, and performance in one of the harshest environments humans have ever entered.
Yeah!
That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.